Okay, thanks, Yuval. Good afternoon, everyone. Let me start by thanking all the organizers for giving me this opportunity to speak in this wonderful meeting. I'll be talking about quantum state steering using weak quantum measurements. What I mean by quantum state steering and what I mean by weak quantum measurements, I will explain as I go into the talks. Okay, so by looking at the current progress into the field, particularly from the experimental side, it is more or less clear to say that we are entering into the quantum information era, where experimentalists and the companies like Google and IBM, they are building multi-qubit processors and are doing exciting experiments. So a typical quantum algorithm involves many stages. For example, first one need to initialize the system into a specific state. Then one has to do a bunch of gate operations. And then at the end, one has to do the measurement to read out all the result of the computations that processor did. So in this kind of setup, the whole role of the measurement is just to extract the information out of the system state. On the contrary, there is an idea of using measurement as a tool to manipulate the quantum states. So in this kind of setup, once you initialize your qubits or system into a specific state, then instead of doing the gate operations, you do a sequence of measurements, particularly weak measurements. And as we know that the measurement comes with a back action on the system state, so a sequence of weak measurement will induce a sequence of measurement back action on the system state. And this way, one can manipulate the quantum system in a desired manner. So here, the role of the measurement is not to extract the information out of the system state, but to manipulate the quantum system. Today, I will focus on this kind of strategy. But before I do that, let's recall what do I mean by quantum measurement. So when we learn quantum mechanics in the very first lecture, we learn about its postulate. And one of the postulate does talk about quantum measurement. It says that if you have a system in some state, for example, a spin half system, which is a superposition of spin being up and down. And then when you do a measurement, in this case, I'm doing a sigma z measurement. So the system will collapse either to the up state or to the down state. And this collapse happens instantaneously, and this collapse happens probabilistically. This kind of measurement are known as projective measurement or strong measurement. Apart from the strong measurement, we also have weak measurement, where the situation is more tricky. So here, the system is coupled to an ancilla using some Hamiltonian that operates on the joint Hilbert space. And this Hamiltonian will create an entanglement between system and the ancilla. And now, when you measure the ancilla projectively, following the concept of entanglement, it will induce some back action on the system state. Now, how much the back action it will induce depends on the strength of the entanglement. And in the weak measurement scenario, the entanglement is usually weak. And because the entanglement is weak, the measurement back action will also be weak. So if you start in some superposition state, you will end up in some different superposition of state with slightly modified coefficients. So following the measurement as a tool to manipulate the quantum state, one can address different questions. For example, one can investigate the problem of quantum state engineering, where the aim is to prepare quantum states using a sequence of measurements. Additionally, one can also investigate the problem of measurement-induced phase. We all know in condensed matter that when a system evolves in a closed loop under a Hamiltonian, it acquires some phase. That phase can be a dynamical phase or geometric phase, or if the Hamiltonian has some fluctuations, it can also acquire some dephasing. And the goal here is to replace the Hamiltonian dynamics with the measurement dynamics. And the question is, what happens when the system evolves in a closed loop under the measurement dynamics? Will it acquire some phase? If it acquires, what type of phase it is? Another interesting problem one can address is about the open quantum systems. Open quantum systems, particularly the non-Hermitian Hamiltonians, are quite popular these days. And the question is how to implement them in an experiment. And measurement is a way to do that. Measurement is one of the ways to do that. Today, out of these three interesting problems, I will focus on the first one, which is the quantum state engineering using weak measurements. Okay, so what do I mean by quantum state engineering? We have a system which is in some state, we don't know its initial state, and we want to prepare this system to a specific target state. And the target state can be a pure state. Then we will denote the target state using some wave functions. or it can be a mixed state. In that case, we will denote it by density matrix. And this whole process of taking an unknown initial state and steering it to the desired target state is known as a quantum steering. There are ways to prepare quantum states. One of the ways is to use projective measurements. So for example, if you have a spin half system in some superposition state and you want to prepare it to the up state, the simple method is to do a projective measurement of sigma z. So sometimes the system will get collapsed to the up state. When it gets collapsed to the up state, very good, we have our target state, but measurement is probabilistic, and sometimes system will also collapse to the down state. So in that sense, the success in this kind of protocol is not guaranteed. So if the system collapses to the down state, the simple method is to apply feedback and take it back to the up state. But with the feedback, you have to be very fine-tuned. Otherwise, you will not end up in the target state. You will end up in some vicinity of the target state. There are also problems when you deal with the larger systems, because with the larger systems, you have a larger set of possible outcomes. And for each measurement outcomes, you have to apply a different feedback. Therefore, your problem becomes more complicated. And also, there's an issue of robustness. If you go to any experimentalist lab, they will tell you that we don't work with perfect systems, we have noise. And if you have noise, then this kind of methods fail quite badly. The alternate method is the thermalization, where you have a system and you want to prepare it to its ground state. So the simple method is to couple it to a colder bath, so that the system will get cooled down to its ground state. But when you are dealing with the larger system, it might happen that the energy gap between the ground state and the first excited state is not much. So if you really want to prevent all the thermal excitations, your bath has to be much colder, which is a challenge in itself. So we are looking for a protocol that should give us a guaranteed success, and we should not need any fine-tuning in our protocol. And we should be able to target any state, whether it's a pure state or it's a mixed state. And our protocol should carry a reasonable robustness against the external perturbations or noise. So I will present a protocol that will use weak measurement, and that will satisfy all of these criteria into the checklist. So the rest of my talk is structured as follows. First, I will talk about quantum measurement, a detailed description of quantum measurement. Then I will give an example of single qubit state engineering protocol. Then I will show some experimental data from our collaborators' lab. And in the end, I will summarize my talk. So when we talk about quantum measurement, typically we talk about von Neumann model, which contains 3 steps. The very first step, we take a system and we couple it to the detector. And note that the detector is prepared in a trivial state. It's always prepared in a trivial state. That's easy to prepare. And the system is in some unknown state. We couple the system with the detector using some Hamiltonian that acts on the joint Hilbert space. So this Hamiltonian will create some entanglement. And once the system is entangled with the detector, we measure the detector, a local measurement on the detector Hilbert space. So because the detector is a spin half object and it's prepared in the up state, if we measure the sigma z observable, detector state might get collapsed to the up state, or it might get collapsed to the down state. So when the detector state gets collapsed to the up state, we call it a no-click measurement, because the detector state hasn't changed. If the detector state is get collapsed to the down state, we call it as a click measurement. These are just the name. You can call it in other words. And then we reset the detector again to this initial state up, and we repeat the whole procedure for the next measurement step. So a given measurement steps contains these 3 steps. Going into mathematics, we take the detector, we denote it is by phi. Here the phi is up, and we denote the system state with psi. And before we do anything, we write the joint state as the tensor product of these 2 in the joint Hilbert space. Then we apply the Hamiltonian evolution so that the system gets entangled with the detector. Then we do the measurement on the detector, and because our system is entangled with the detector, any local measurement on the detector Hilbert space will create some back action on the system Hilbert space or on the system state. And this back action could be different depending on the measurement outcome. So in my case, when you have a no-click measurement, our system gets a small back action. When you have a click measurement, our system gets a large back action. And this back action can be beautifully represented using the Lindblad jump operator in the both sides. So when we say that we are not bothered about individual measurement result, we want to do the averaging. When we average over all the measurement outcomes, people call it as a blind measurement because we are blind to the measurement outcomes. Then we no longer have the pure state, we have the density matrix because we are averaging over measurement outcomes. And the evolution of this mixed state or the density matrix of the system is governed by the master equation. The first two terms in the master equation comes from the no-click measurement. You can visualize it. The third term comes from the click measurement. And the alpha is a parameter that comes in the Hamiltonian. This alpha somehow controls the measurement strength. So now let's focus on this evolution equation. We all know that this is a dissipative evolution equation. And every dissipative evolution equation will take the system to some equilibrium state after a very long time. We can find the equilibrium state by equating the right-hand side to 0. And which equilibrium state it will end up depends on the Lindblad jump operator. Or in other words, it depends on how you entangle your system with the detector. So if you want to prepare your system, or if you want that your system at the end of the day ends up in a specific target state, you have to be very careful on how you entangle your system with the detector. So if you want to prepare your system in a specific state, you have to take a step back and design a careful Hamiltonian. Now let's look up an example. So here, consider a trivial example of single qubit. Any single qubit state can be visualized using a Bloch sphere. There are states on the surface of the Bloch sphere. We call it as a pure state, and there are states inside the Bloch sphere. We call them as a mixed state. So first, let's consider the example of the pure target state, which is up, which is the north pole of the Bloch sphere. For that, you have to couple your system with a detector using the simple Hamiltonian, sigma x onto the system and sigma x onto the detector, plus sigma y onto the system and sigma y onto the detector. With this Hamiltonian, you get the jump operator, which looks like a up and down, the outer product of up and down. And if you see the steady state of this evolution equation, it comes up as a up. And you have to note here that this steady state does not depend on the initial state. So you don't have to know the initial state of the system. Still, you get, at the end of the day, you get your system prepared into a specific target state. Now you can ask, okay, pure states are easy to prepare. There are other methods. What about the mixed state? Well, with the mixed state, you have to combine whatever I told you about the measurement evolution with a Hamiltonian evolution. So for the single qubit systems, it's reasonably easy to solve by considering a most general Hamiltonian for a two-level system. So there are 4 parameters now, omega, alpha, theta, and phi. And the steady state of this evolution equation lies on the ellipsoid. This ellipsoid is fully confined within the Bloch sphere. The top point of the ellipsoid touches the north pole. This means the top point of the ellipsoid is a pure state. Bottom point of the ellipsoid touches the center of the Bloch sphere. This means it's a fully mixed state. And there are other states which are mixed state. Now you choose a specific set of these parameters, omega, alpha, and theta, phi, and you will end up, or your system will end up in a specific point on this ellipsoid. You can ask, okay, what about the other states? What about an arbitrary mixed state? There are other states on the Bloch sphere which don't lie on the surface of this ellipsoid. Can you target them? And the answer is yes. For that, remember I told you in the beginning that detector is prepared in the up state, but no one prevents you to prepare your detector in some other state. So most generally, you can prepare your detector along any axis where M denotes the axis. So if you prepare your detector along the z-axis, which I did in the beginning, you get a blue ellipsoid, which is pointing towards the z-axis. If you prepare your detector in the y-axis, you get ellipsoid pointing in the y-axis. If you prepare your detector in the x-axis, you get ellipsoid pointing in the x-axis. So in this way, you can cover the whole interior as well as the surface of the Bloch sphere. In other words, you can target any state irrespective of its purity. You can target using this protocol. And as I told you, each specific choice of the parameter takes you a unique point on the Bloch sphere, on the steady state ellipsoid, but the converse is not true. As you can see it from this image, that this red dot lies on these 3 ellipsoid. This means there are at least 3 set of parameters that can take your system to this red dot. The question is, which out of these 3 set I should use? And whenever we have more than one way to do anything, we can ask the question of optimization. So here, what I mean by optimization is that I should use a specific set which takes my system to the target state in the least possible time. So I want to make my protocol the fastest protocol. So I want to do the optimization now. How do I do that? I go back to my evolution equation. It's a 2-level system and it's an open dynamics. So we can rewrite the dynamics using the super operator. In this case, because we are dealing with the 2-level system, our super operator is a 4x4 non-Hermitian matrix. It can be diagonalized. And it has 4 eigenvalues. One of the eigenvalues is 0 because our evolution equation has a steady state. So there are 3 non-zero eigenvalues, and out of 3 non-zero eigenvalues, 1 eigenvalue is purely real, and there are 2 complex eigenvalues which happen to be in complex conjugate pairs. And we are interested in the real part of the eigenvalues because the real part controls the decay rate. To be more specific, we are interested in the smallest real part because it is the part which controls the convergence rate at a longer time. So if you want to do the optimization, we have to tune the parameter in such a way that the smallest real part becomes maximum. What? Yeah. 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 Okay, so we do this numerically. We take states with different purity and we vary the free parameter in the protocol, and we focus on the smallest real part. So as I told you, there are 3 non-zero eigenvalues. 2 of them happens in complex conjugate pairs. So green and red are complex conjugate pairs. So you see only red solid line, which is the real part. And the blue part is the real eigenvalue. And we are interested in the smallest eigenvalue, which is the real, which is the blue line. And we are interested in at the point where its magnitude becomes maximum. So for this particular purity, the optimization happens at that value of omega, which is the free parameter in the protocol. We take the state with different purity, and again, we see where does the smallest real part becomes maximum. And it happens that the real part of the eigenvalues cross each other, and at the crossing, the smallest real part becomes maximum. We take state with other purity, and again, the eigenvalues, the real part cross each other, and the optimization happens at the crossing. But here you have to note that not only the real part, but the imaginary part also becomes 0 when the protocol is optimal. This is not the case here and here. We scan this numerically for the whole purity regime, and what we find out is that the optimal steering rate behaves like this. For the smaller purity, it increases as we increase the purity, then it saturates, and then it falls down. So in this parameter space, our optimal steering rate makes 3 different regimes: low purity, medium purity, and high purity regimes. In the low and medium purity regimes, the imaginary part of the eigenvalue survives, which means the dynamics is oscillatory. In the high purity regime, at the optimal point, the imaginary part of the eigenvalues becomes 0, which means the dynamics is relaxational. And the crossing from medium to high purity regime happens at an exceptional point. Exceptional point is a beautiful feature in the non-Hermitian physics. So exceptional point is the point where the eigenvalues as well as the eigenvectors collapse onto each other. And there's a dynamical phase transition in the system dynamics being oscillatory and being relaxational, and this dynamical phase transition happens at the exceptional point. And there are similar connections that has been observed that the optimal behavior of the protocol is related to the exceptional point in other settings as well. For example, these two papers talks about the same phenomena, but in thermal machines. This tells us that this relation of the optimality and the exceptional point is not specific to this problem, but it is kind of universal. It happens in other settings as well. Okay, whatever I have told you right now is just not a fake story. It's a real story that can be observed into the experiment. So there are experimentalists. There is an experimental group into Weizmann Institute that works with trapped ion systems, and they saw that the measurement-induced steering indeed can stabilize pure in the mixed state. And here I plot the infidelity, which is 1 minus fidelity, and you can see that all of the target state protocol can reach to the target state with a fidelity of at least 99%, which is quite good in my opinion. Okay, so what are the key takeaways from my talk? The first key takeaway is measurement-induced backaction is not something harmful. It can be used to study interesting phenomena. The second one is the optimal steering happens at an exception point, and we saw that this connection of the optimality and the exception point is not something specific to this problem. It happens in other settings as well. There are future outlooks. One, I talked about single qubit state steering. One can talk about multi-qubit state steering. Yuval did a work which talked about AKLT state steering. And one can also use measurement-induced backaction to design some quantum gates, which would be quite interesting. One can also talk about that I'm not interested in stabilizing a specific state, but I'm interested in stabilizing the whole subspace. And once one can achieve this capability, one can also talk about dissipative phase transitions using measurement-based evolutions. And also the measurement-induced steering is just not a theoretical concept, can be observed into the experiments. Before I end my talk, I would like to thank a few gentlemen who collaborated onto these projects. Yuval, Kirilo, Bernd, and Igor are among the audience. So if you don't find me, please guess them to ask your questions. And Ed is Yuval's PhD student who is in Weizmann. Roy and Yotam are the experimentalists who works with trapped ion systems, and they did their experiment based on our work. With that, I would like to thank you for your attention.
So you said that when you don't have a back action, so if you go to one of your first transparencies, there was something with the square root of dt in there that really confused me.
Yeah.
Yeah, that one. The large back action. How do you get a square root of dt from quantum mechanics?
Okay, so this square root of dt, it's some kind of mathematical trick. It comes, you see here the alpha, and maybe I write it again in some other slides. This alpha is j square times dt. J is the coupling of the Hamiltonian. So this dt is not actually square root dt, it's j square times dt square, which is j times dt. But you do a clever rescaling to go into the weak measurement regime. You scale your coupling in such a way that you get this kind of effect here.
What is the question?
Thank you. It's just to make contact to previous talks. I mean, can you say something about quantum steering, for example, fractional quantum Hall states?
I'm sorry, I'm not a condensed matter condensed matter specialist.
Well, I mean, my question is, can you stabilize, for example, a Laughlin state using quantum steering?
What?
Yeah, let me take this question. So there is actually a paper by the authors are Alex Kamenev and myself 2-3 years ago in Nature Communications. So the idea was that there is some approximate a matrix product state in 1D, which approximates the Laughlin state. And then we show how we steer towards this one-dimensional thing, including the degeneracy, the threefold degeneracy if you have mu equals say 1/3. So on this level, it has been done.
My question is precisely related to the issue of complexity. You know, if you start from this local representation, of course, you can always, you know, map through Jordan-Wigner, you know, to fermions, whatever. But there should be some problem, you know, of known locality that shows up in the complexity of steering those known local states. So that's the reason why my question is, if you try to do that, in principle, you can do for a few ones, but what is the complexity of doing that?
Good question, open question.
We don't know. Yeah.
I would like to make a comment regarding the square root of dt. So in my understanding is it's a mathematical trick in the sense of an Ito differential. If you have some random walk-like process where you have to take into account then a derivative of the function and so on. That's all I believe. Yeah.
Diffusion or stochastic processes.
Ito calculus, that Wiener increment and all that stuff.
Yeah, the term steering was coined first by Schrödinger in 1935 after the EPR paper. So quantum steering is something like you can prepare the Z ensemble, you can prepare the X ensemble by acting on one side. But steering, you are using steering in a different sense, like some kind of measurements, back action on the system.
Okay, so what you are saying is also related to what I do.
Let me finish my question. And secondly, weak measurement has a well-defined, has been well-defined by Aronov and this Weizmann. So are you telling about weak measurement in their sense?
No, they talk about weak values, which involves post-selection and pre-selections. That's not what I do. And regarding the first question, there is, you can ask about the meaning of steering, but if you think carefully, here also steering carries the same meaning. Like you have the entangled parties, you do something on the one party, it creates a back action on the other party. I'm calling it as a measurement back action because I'm coupling my system to the detector. In principle, you don't have to do that. You can take Alice and Bob, couple them, do something on the other part, do something on one of the party locally. It will create some back action on the other party. That's also, I think, you are talking about steering. Yeah, but here we don't do that. And I think he has.
There is a question over there.
So yeah, so my first question is about the exceptional points. So each exceptional point comes with a specific order. So does the order of the exceptional point appear in any calculable or observable?
Yeah, so here the exception point which I talked about is a third order exception point.
Okay.
We had 3 non-zero eigenvalues, all of them merge onto each other.
And does the order appear in any calculations or in any observable? Okay. And what determines the rate at which the dynamics moves towards the final steady state? So how is that constrained? The rate of dynamics towards the steady state?
Depends on several parameters. It happens that once you choose a target state, so I showed that there are 4 free parameters into my system, but once you fix the target state, 3 of them goes into that. By fixing the target state, there remains only 1 parameter, which is the ratio of the Hamiltonian rotation and the dissipation that is caused by the measurement. And you have to tune these free parameters that controls the decay rate.
Okay.
And you have to tune it in such a way that the decay rate is maximum.
Okay, thanks.
So I had a very basic question. So here you're doing 2 things. You are entangling with a pointer or something like some ancilla, and then you're doing a weak measurement. So the way you entangle is also like not fixed in your protocol, and the weak measurements are also variable. Like isn't it too many variables? Like, how do you fix inside a given ellipsoid when you're allowed to do so many things? Like, you can vary how you entangle, you can vary how you measure. So isn't it a lot of variables?
This entanglement comes inherently when you try to do a measurement. So when you try to do a measurement, you have to couple your system to something. And this coupling in itself creates an entanglement, because if the system is not coupled to any external object, you cannot do a measurement. So the measurement in itself carries all this complexity. And now you are asking that the measurement is a complex thing to do. I agree with you, but this is what experimentalists do.
And one more question is, you wrote the master's equation, the Limblad equation. So can we find out weak measurements with the gamma, with the coupling there, like with the gamma that's there in the equation? Like, does that tell about whether a measurement is weak or not? Like, does it have a relation?
It will have a relation. There involves a couple of mathematical steps, which I didn't show here. I can explain you when we talk about over coffee, but yes, there is a relation. That's talks about weak measurement.
I have a mathematical question. So in this master equation, so it's an existence uniqueness thing. Like, so you have unitary dynamics, you also have dissipative dynamics. So firstly, like, how is it guaranteed that a steady state will be reached? And if a steady state is reached, is that steady state unique? I mean, there could be other steady states in solutions to the same equation.
Very nice. In this case, the steady state is unique. And why it is guaranteed to reach to the steady state? Because the evolution is dissipative in itself. So any dissipative evolution will end up to the equilibrium state after a very long time.
But in some other case, it could have a manifold of steady states.
That's an interesting open question. I talked about in the summary slide that yes, you can ask that I don't want a unique steady state. I want a manifold of states that are steady state of my evolutions. Yeah.
I see.
I had a question. How are you doing optimization?
How I do optimization?
Yeah. Which technique shall you do?
Can you repeat the question?
He is asking, how do I do the optimization? So as I mentioned, the protocol, how fast the protocol will converge to its steady state, that depends on the eigenvalues of the evolution operator, which is the super operator in this case. Now the idea is to maximize the smallest decay rate by tuning the free parameter into your protocol. That's what I do. I vary over the free parameters and I look for the values at which the decay rate becomes maximum.
So, questions? Thank you very much.